Okay, good morning, class. This is the video for the September 3rd class, and in it this may be a little bit short. I'm just going to cover the section on doping and conductivity of semiconductors, and finishing that up basically, so that I can give you homework on that. And given the discussion during the chat session yesterday, I'm going to first back up a little bit and include a discussion of electrons and holes that's not in the handout. I think you got the gist of it during the chat session, but let's just go through it. So semiconductors. So let me write this down. Pure semiconductor. Conductor. So oops. So as we went through yesterday during the chat session, an example of a pure semiconductor is silicon. So silicon is group 4. So that's 4 valence electrons. And so that means that, if you remember your chemistry, you probably didn't go over solids in your chemistry, you went over molecules. And so you learned how to do the octet rule in forming molecules, that every atom in a molecule likes to have 8 valence electrons around it. And it's the same for a solid. And so for a group 4 solid, that's very easy because you just form an array of silicons. And so each silicon atom has 4 valence electrons. 1, 2, 3, 4. And so if it's bonded to 4 other silicon atoms, and now of course in the textbook we will cover that things are bonded in 3-dimensional structures, such as silicon. So this is just sort of schematic here on the board, showing them bonded in a plane here. But basically, each of those 4 silicon atoms contributes a valence electron. Okay, so any particular silicon atom has 8 around it, and so by the octet rule, which in chemistry, you learn that that's due to the fact that there's these things called orbitals. If you do actual quantum mechanics, you discover that that's because a group of 8 like that forms a stable quantum mechanical shell. But either way you look at it, it likes having 8, and so you can form a crystal with silicon where it's bonded to its 4 nearest neighbors, and so each silicon has 8 valence electrons around it. Now, this is basically an insulator, electrical insulator at T equals 0. Of course, that's Kelvin. And the reason why is because all the electrons, all the valence electrons, are bound up in bounds, and so they can't move. And so if I put an electric field on this solid at 0 Kelvin, none of these electrons are going to move. Now we'll talk about in a little bit what happens as you raise temperature, but let's keep the picture at 0 Kelvin here so we can explain doping. So here we go to a doped semiconductor. Okay, and let's draw our silicon crystal, which, by the way, when you have a regular array of atoms like this, it's called a crystal. let's replace one of the silicon atoms with arsenic. Arsenic is group 5. So it has 5 valence electrons. And so what happens, well, okay, so basically let's start drawing our picture here. All right, and you know, the neighboring silicon atoms, they contribute their valence electron like usual. And there's an extra one here. Now, if you, you know, go through, you know, a full development of semiconductor physics, you talk about that extra valence electron being in a quantum mechanical state, and you talk about conduction in valence bands and things like that. But for purposes here, I think everyone can appreciate that it's pretty easy for that extra electron to come loose and act as a conductor. Okay, so this can conduct then. Okay, and so the electron can conduct, and since the charge carrier that forms conduction is an electron, it is called n-type, because the charge carrier is negative. And to achieve levels of conductivity required in semiconductor devices, you only have to replace like maybe 1 out of 1,000,000, or at the most 1 out of 1,000 would be very heavy doping of the silicon atoms with arsenic. So that's n-type. Now, if instead, let me think of a good, let me do boron, because that's a typical, try to make my array like it is before. Okay, so now let's put boron. Boron is group 3. And so it has 3 valence electrons. And so if we start drawing our picture here, 1, 2, I'll put it down here. There's its 3, and here's the neighboring silicon with its, you know, contribution. And you see that there's this missing one here, and so a bond is missing a valence electron. And you know, I drew a circle around it so it looks like a hole, and in fact that's exactly how it behaves. That if I put an electric field on here, I can make like that electron move into, well actually it's more like that electron move into that bond, and then an electron from down here can move into that bond, etc., etc. And you know, the way I was taught this, and I think, you know, the easiest way to look at it, like I explained yesterday in the chat session, is that you have like a billiard or pool table, and you know, insulating silicon is like that pool table filled with billiard balls, you know, completely, and none of them can move because it's all filled. If you take away one though, all right, then you can start moving the balls around and stuff like that. And so if you do that, it looks like there's this hole moving around in time. And in fact, if you go through semiconductor physics, you can exactly treat that missing electron as a positively charged particle. And so this is p-type. And, you know, I mean, so formally, you can write F equals ma, like we did it in the first lecture, for that missing electron as if it were a particle, positively charged. Now, having mass. Okay, even though there's nothing there. And of course, when I put an electric field on this, what's really moving around are all these other electrons. But it has the aggregate effect that an electric field placed on, if I put an electric field in that direction, all right, remember electric fields go from positive to negative, it will act like it's pushing that hole in this direction and causing conductivity based upon a positively charged carrier. And another analogy, which is a little bit more difficult to see, probably more accurate, is a bubble in water. And to use that analogy, you have to imagine that you've somehow turned gravity off. People up in space could do this experiment if they could make a swimming pool. If you were in a swimming pool in a weightless condition and you somehow formed a little bubble in the water, okay, that bubble, of course it could be air, but effectively it has zero, there's nothing, it's nothing in the bubble. But if you pushed on that bubble, it would feel like there's something resisting your push, that F equals ma works. And what's really happening when you push on the bubble is you're kind of pushing on all the water aside. But for all intents and purposes, you can treat that bubble in water as a particle, obeying F equals ma. So that's electrons and holes and n-type and p-type. And n is the number of electrons per unit volume, and P is the number of holes per unit volume. I'm going to use what I've drawn here to additionally kind of explain things at this point, because of course there are semiconductors other than silicon. And so I'm not going to draw another, well, should I draw? No, I'm going to keep my pictures, but just as an aside, okay, I'm going to make another semiconductor. And you get the idea, it's the same idea. For any semiconductor I make up, I can cause it to be p-type or n-type. And so let me make another semiconductor. And let me make it gallium arsenide. Okay, gallium is group 3, and arsenic is group 5, as you know. And so this contributes 3 valence electrons, and this contributes 5. And so it's the same picture as far as the rule of 8 goes. Because this gallium contributed 3 of them around it. And the arsenics, okay, so you have to kind of use a Gestalt kind of understanding here of how these valence electrons get distributed. But basically, every gallium arsenide here, every arsenic atom can contribute 5 of them. And so if you look on an overall basis in the crystal, you have a total of 8 valence electrons for each pair. And so you're able to put 8 around each one. And so you're able to form the same type of bond for gallium arsenide as you did for silicon. And in fact, when we cover crystalline structures, you'll see that it's almost precisely the same type of bonding. It's a tetrahedral arrangement. It looks very, very similar to silicon. In fact, it is exactly silicon. It's called a diamond structure, just with gallium arsenide instead of all silicon. And so there's what's called 3 5 semiconductors. All right, and I have to kind of remember my periodic chart here now. I should have this by memory, but well, let me think. Okay, what's to the right of arsenic that I can use here? So it'd be group 6, and on the left, you know, I think I remember one. Okay, I may be wrong here, but for illustrative purposes, cadmium, telluride. Okay. This may be not exactly right, and I should have. Okay, but you get the idea. I'm not sure I got my atoms right here, but you can have where you form a crystal like this using group 2, which I think cadmium's group 2, and telluride, which is group 6, I think. And so you can have a 2,6 semiconductor. And let me erase that quickly because it might be wrong. I should have been sitting here with the periodic table in front of me. And, you know, lithium fluoride. Oops, the way around. Lithium fluoride, lithium, fluoride, lithium, fluoride, lithium, fluoride, lithium. Okay, and so this is now group 1, and this is group 7, and so you can also have a 1,7 semiconductor. Now, as this becomes more one way and not the other way, they become less useful as a semiconductor, and the reason why is because it becomes much more difficult to perform things like doping and things like that. Let's just put it that way for now. But you get the idea that you can have other types of semiconductors, and you can have variations on this thing too. And so there's a lot of semiconductors that are potentially possible. Now, generally, of course, 90-some% of our electronics is based on silicon. Some of the rest, particularly some of our optoelectronic devices like lasers and detectors and things like that are based on gallium arsenide or indium arsenide, another 3,5 semiconductor, or indium phosphide. Things, other semiconductors like mercury cadmium telluride, which is what I was kind of remembering that one, are you know, for infrared detectors, and so you know silicon, germanium, which is another group 4 material. Less than that carbon. One of the things I'm going to have to deal with, and that every class has to become aware of, is my cat. This is grits. Okay, stay away. But as we go through the course, and particularly when we talk about crystalline structures and things like an epitaxy, we'll return to understanding these different types of semiconductors and how you use them. All right, so let's go back to silicon. Silicon, 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 silicon. And silicon. All right. And so you have these 8 electrons around each silicon atom in the crystal, 8 valence electrons. And so it's a very stable crystal, very stable solid. And at 0 Kelvin, as discussed, um, it has zero conductivity because all the valence electrons are locked up into the bonds. And so if you put an electric field on them, none of them can move. Now, what can happen, what does happen, okay, it does conduct at T greater than 0, like at room temperature, and it does so because one of those carriers, one of those valence electrons can gain enough thermal energy to rip off of its bond. And so what happens then is that you form both a hole and an electron. So that's why I was saying yesterday, someone asked during the chat session, well, why do you have to take into account both N and P? Isn't it one or the other? And well, okay, so here's the first example. And this is, another word for pure. There are several words for pure. Another word for pure could be undoped, and that's easy to understand. And another word is intrinsic. The word, like I said, undoped is pretty easy to understand. Pure, same thing. Intrinsic, actually, I'm not sure where that word came from. It has sort of a plain meaning in the English language. It means something as it is intrinsically, meaning as normally. And I guess you just say that silicon, if it's intrinsic, you haven't done anything to it, like put in dopant atoms. But that's just a word there. So, so thermal energy can cause one of those electrons to rip off the bond, leaving behind a hole. And so you have both N and P. We could, that process, for those of you who have taken semiconductor physics, know that what's going on here is that you've moved an electron from the valence band to the conduction band. I don't want to start writing down things like that because that's not necessarily, things like band gaps. I'm trying to think ahead in time. It's analogous to making dishes in the kitchen. That to a certain extent, you don't need to know the chemical makeup of cake in order to make a cake. It's helpful, perhaps. Here, for this course, and it is a little bit of an oddity that ELEG 422622. To a certain extent, you don't need to know certain things about semiconductor physics in order to make semiconductor devices. What I'm giving you here is the basic things that you just do have to know. Now, getting back to this, if you were to go deeper and try to understand what's happening more, you would learn about valence bands and conduction bands, and you would learn that when at room temperature or some temperature above 0, the reason why you have electrons in holes is because if you look at the thermal distribution of energy, and that's called a Boltzmann distribution. Well, it's a Fermi-Dirac in here in this case, but all it means is that at room temperature, and we do have to know this to a certain extent, I think. There's something called KT, which is the thermal energy. Now here K is Boltzmann's constant, and T is the temperature in Kelvin, of course. And that's 0.026 electron volts at T equals 300 Kelvin. So the average thermal energy, and we talked about thermal energy in the context of Ohm's law a little bit yesterday. At room temperature, 300 Kelvin, is 0.026 electron volts. And you know, an electron volt is the energy an electron acquires passing through a voltage, a potential of 1 volt. I'm not going to get into a whole discussion of energy units and things like that here. If someone needs to understand that better, contact me offline. But that's the average thermal energy. Now, this energy to rip an electron off the bond is around 1 eV. And by the way, that's the band gap. For those of you in the know, as far as understanding what that word means. Now, you may think, okay, that's a lot smaller than that, and it is, but you have to understand that all the electrons in this solid have a distribution of energies whose maximum is at points, that's its average value. Okay, but just like the air molecules in this room, okay, the average energy is whatever it works out to. Well, no, same thing. Okay, there'll be a very small probability that some electrons will have that much energy, just because there's a whole distribution. So we could talk a lot more about that, but it means that there's a very small amount of these, N and P, that happen at room temperature. Okay, now now's a good time in the discussion to talk about that a little bit. Let me erase this here because you get the idea what atoms you dope with. Now, for N-type, so the way I want you to understand this is that, okay, no matter whether, which by the way, another word for is extrinsic, whether it's undoped or intrinsic or doped either way or extrinsic, the way I want you to think about this is that there's both electrons and holes, there's both N and P. So of course if it's N time, it's mostly N. That is, you know, N is much bigger than P. If it's P type, it's, you know, P is much bigger than N. But for any doping, the product of N and P is a constant. And we'll talk about what that constant is in a second. But what I'm telling you is that, okay, if I start with an intrinsic, there's a certain number of N, you know, small number, and P is equal to that. Remember, for intrinsic, every time you make an electron, you make a hole. So, I mean, actually I should put, for intrinsic, And I know this is getting a little bit messy here. All right, and so N times P is some number for any particular semiconductor. And as I vary the doping, let's say I add in N-type doping, well, N's going to get bigger, but P is going to get smaller. But their product is going to remain the same. Now let's do this for intrinsic, which means undoped. N is equal to P. Okay, again, all right, you understand why that an intrinsic semiconductor, I get N and I get P because I thermally rip electrons off the bonds, and that means that every time I do that, I leave behind a hole, so they're equal to each other. The intrinsic and thus for any the product of NP is then Ni squared. Why? Because I told you that for any doping, the product is a constant, and since for the case of no doping, they're both equal to Ni, their product is Ni squared. Now, this comes from, let's see, 1, 2, 3, 4, maybe 5 lectures in semiconductor physics. And for those of you who have taken semiconductor physics, you know that it comes from the fact that you have Fermi levels relative to the conduction and valence band, and as you vary the doping, you vary the Fermi level, but as you vary the Fermi level in one direction or the other, it works out when you do the quantum mechanics and stuff that N times P is a constant. So let me put a box around this. Now, why is this important? Okay, so this rule, okay, that if I take any semiconductor silicon and I dope it in any way, okay, I could put both boron and arsenic in it, okay. Np is equal to Ni squared. Now, why is this important? Well, it's important it's an incredibly important principle in semiconductor physics because it allows you to solve lots of problems. But besides that, in this class, you will see that from time to time we are going to refer to N sub I. N sub I is something you look up basically. There are tables of it. Now, you do realize that N sub I is a function of temperature. So, because the higher the temperature, the higher this is going to be. And so, in the textbook, you might find certain tables that list N sub I, the intrinsic carrier concentration, at, for example, 300 Kelvin. And so it's a parameter you have to learn. And, I'm trying to think of something analogous in the kitchen. It's like the density of cake or something like that, that that might go into all of your process formulas. And so it's a concept you have to be aware of, whether you're trying to understand semiconductor physics and devices and how they work, or you're trying to make them. And so it's important for both classes. So I think we've beat this to death. We've established it. We know about electrons and holes and things like that, and we can go from there. Now, going from there is picking up where we left off on the last lecture now. All right, and let me check my time. Good. All right, and where we left off was, I'm just going to write down a few things. I mean, J equals sigma E. Okay, that's microscopic Ohm's law. J is the current density. Which is I over A, current per unit area. This, of course, is the electric field. Which is, given by V over L, voltage over length. You can think of it as this is sort of how sigma, the conductivity, is defined. And in the notes, I show how you connect that to the usual Ohm's law you thought of as, which is V equals IR. Now, there's an ancillary formula, and I'm going to make sure, when I write V, that's voltage, and then the little one is little v. And I'll preface this. The drift velocity, remember, all the electrons in the solid have both thermal and drift velocity. The thermal velocity is there even and it's much larger than the drift velocity, which is due to the electric field. Now this is a definition. Okay? Where mu is the mobility. So, when you draw three lines like that, that means that this is defined, right? It's not something I derived, it's the definition of what mobility means. And it makes sense, right? Because the higher the mobility, the higher velocity for a given electric field. So it's more mobile. All right, and you put those together. Well, we derived, okay, that J is equal to E N times V drift, and that comes from a flux analysis. Flux analysis. It's interesting to me that I use the concept of flux in almost every class I teach. The next lecture, I don't know if we'll get there today, but calculating the power in wind use flux analysis. So it's just this kind of universal thing. It's something that is not only not really taught ever well, but it's hard to teach. But let me put it a little aside here. Okay, this I run into my wall over here. This is okay. Remember, J is current per unit area. So this is the charge per unit area per unit time. right? Because current is charge per unit time. So J is charge per unit area per unit time. That's the flux of charge. That is, that if you looked in a three-dimensional situation and you made a plane, okay, that it would be the amount of charge, a quantity of charge, passing through a certain area plane in an amount of time. And you know, that's equal to the flux analysis is that's equal to the charge per unit volume okay, times the velocity. All right, of the charge. All right, and you can see that the units work out right. And you know, that's enough for most people, but I mean, you know, if someone really wants to walk through flux, it's worth doing, because basically this formula, it works if you replace charge with anything. You could replace it with pancakes, okay? If there were pancakes flying through the room, the number of pancakes going through a certain area in an amount of time would be the density of pancakes, okay, times their velocity. Okay, so you know, that's the powerful, and so we do the same thing when you calculate the power and wind and things like that. So you know, you can replace charge with anything here. And now the velocity of the charge is the drift velocity. It's not the thermal velocity, right? The thermal velocity is the you know, the electrons, you know, bouncing around everywhere. So there's no movement in any particular direction. It's only when you have a drift of that charge that you have a velocity of it. And the charge per unit volume, okay, that's this. Okay, why? Because N is the electrons per unit volume, and E is the charge of an electron. All right, now, that's if you only have, and so you put those together, and you write then that J is equal to, look at it, E N V drift mu E. Now that's if there's only electrons, and I think I've really established that there's both electrons and holes. So if there's both electrons and holes, then you just add that term. Okay, now you do have to do something here. I mean, this has to be the mobility of electrons and the mobility of holes, because they're different. And you know, that's not really hard to understand. Even though a hole and an electron have exactly the same charge, just opposite sign, they can have different masses and so have different mobilities. So you have to, you know, make sure that's in the equation. And so that's sigma. Okay, I'm going to leave this up. So we're going to use that now. Because, all right, this isn't enough. Because remember, what we were, the title of the lecture or lectures was Calculate Conductivity from doping levels. Okay, and what are doping levels? Well, they're the concentration of the dopant atoms. So let me make sure I use, because here people tend to vary what variable to use. Okay. Okay. Let me just in silicon. Okay. N sub D is the would be, for example, the arsenic atoms per unit volume. The D stands for donor. Because they donate an electron. But okay, so it's the density of N-type dopant atoms. And N sub A is in silicon the boron atoms per unit volume. And that's for acceptor. Because the boron atoms act to accept a valence electron because they're missing one. You understand that in a different semiconductor, I mean, you know, it might be a different atom here. Okay, N sub D is the volume density of donor atoms, and N sub A is the volume density of acceptor atoms. Now, I did erase my picture of the crystal. Okay. I have to draw it again real quick. I'm sorry. Okay, so let's imagine a donor atom. Okay, it's arsenic here. All right, and I'm not going to draw them all, but it gives up an electron. Okay, it gives up an electron that can go flying off and be, you know, a happy conductor. When it gives up that electron, it leaves behind a positively charged arsenic atom, right? Charge neutrality. And the same thing for, you know, if, let me draw it. You know, if I did boron, okay, and I'm going to, you know, draw it the same way and realize there's electrons moving and stuff like that, really. But if it gives up its hole, okay, it leaves behind a negatively charged boron atom, okay, because it's given up this hole. It means it's actually accepted an electron, so become negatively charged. Now, I know this is, you know, something you have to work through before you become fluent with it. A donor atom becomes positively ionized in the semiconductor, and an acceptor atom becomes negatively ionized, right? And you just have to go on offline and every morning in the shower say to yourself, a donor atom becomes a donor atom becomes positively charged when it ionized. An acceptor atom becomes negatively ionized. Actually, it's kind of easier to understand in terms of the acceptor because it's accepting an electron, it becomes negatively charged. Anyway, okay, we're going to assume all dopant atoms are ionized. That is, you know, we're, you know, at room temperature. You know, for example, or, you know, you get the idea that in any semiconductor we're going to analyzed, there's enough thermal energy to rip off those extra or missing electrons. And so for purposes of this course, we're going to assume that, now I'm going to write something down here. Remember, when I donate, okay, become positively charged. And so that refers to, I'm not going to write it down, the density of ionized donor atoms. And, I'll do that, okay, but, for purposes here, it's equal Na minus the density of ionized acceptor atoms is approximately equal to the actual density of acceptor atoms, meaning they're just all ionized. All right. And now, charge neutrality states that plus equals minus. That's what charge neutrality is. And so we write down the plus side, the holes, plus the acceptors. And I'm not going to bother putting Na minus here because I've told you, we're going to make this assumption that it's equal to, Na by itself. It's equal to negative charge. Let me do it this way, put this plus over here, so that you get the idea that the plus charges are the holes in the acceptor atoms, and on the negative side, it's of course the electrons and the donor. And we're going to stop there today, because with those two equations, if you think about it, you can determine N and P from Na and Nd, and then you could put them in here, and we've done that. But given the doping levels, Na and Nd, okay, and using this equation, I can solve for N and P, and I can plug them in here to get the conductivity. And that'll be your homework. So that's where we're going to end it today, and I hope you found that entertaining. Damn it. Let me see if I can fix this. See, there's a way of, all right, let me do this. Okay, I do apologize and know this is going to be an ongoing issue, which, I mean, if you've noticed, I've tried to monitor my computer screen here. I don't know how to enforce it going into focus on the words. Okay. You see, what happens is that as I what happens is that as I move in front of the camera, it tries to focus on my body, and so it loses the focus on the screen, on the blackboard. And I don't know how, there's like no button I can click here to make it maybe if I walk in front. It just won't do it, will it? Okay, there it's working. Okay, so maybe it looks for a vertical line or something like that. Okay, here we go. All right, so I don't know when it lost focus, but you can see the entire board there. It contains all the information. It shows, you know, I don't want to mess up by pointing things. It shows that we've accomplished the title of the lectures, which is calculating conductivity from doping levels, Na and Nd, and how you do it. With the relevant boxes circled, the charge neutrality equation and the product of Np equal to Ni squared equation, and of course the equation for sigma itself. So it's all there, and if anyone, well, people last spring sent me suggestions of how to keep the camera in focus. They don't work. There's no there's no button here or anything. I mean, maybe different webcams. You know, basically I'm doing this with the webcam plugged into my laptop, and maybe different webcams have some different focusing capability. If someone wants to email me a suggestion, I'm welcome to it, but basically I determined last spring it's just a matter of me trying to keep track of it. It is in focus. All right, well that's it for today. I'll talk to you in quote-unquote class tomorrow.